welcome you all again. So, if you recall, in the last class we did the Laplace transform of a periodic function, and if you see the Laplace transform of a periodic function is like this. If f t is a periodic function with period capital T, say, in that case Laplace transform of f t is equals to 0 to capital T e power minus s t f t dt divided by 1 minus e power minus s into capital T. So, if capital F t is a periodic function with period capital T, Laplace transform of f t, this is equals Laplace transform of f t, this is equals to 0 to t e power minus s t f t dt divided by 1 minus e power minus s t. We did one or two examples in the last class. Today, let us continue with some more example of various type of periodic function, and then we will go to the Laplace transform of some very useful special functions. We will go through this one. Let us take the example that we want to find out the Laplace transform of f t equals modulus of t. If you see f t equals modulus of t is a periodic function with period pi, which is defined by f t equals sin t, where t lies between 0 to pi, and f of t plus pi equals f t. And on the right side you see the graph of the periodic function modulus of sin t, 0 to pi it is there, again pi to 2 pi it is being pure, since periodic is in nature, therefore, it is similarly replicating itself. So, we want to find out the Laplace transform of this function modulus of sin t, where modulus of sin t is a periodic function of period pi. So, let us see the solution process of this function. So, you can write down Laplace transform of modulus of sin t. This is equals, using the formula just now I stated, e power minus s into pi, because pi is the period of the function, then 0 to the period, that is 0 to pi, e power minus s t into sin t dt, e power minus s t into sin t dt. Now, this integral we can evaluate in the normal process, that is, I can say that this is equals to, you can write down 1 minus e power minus s pi into, say, I, where I we are denoting this integral, that is I is equals to 0 to pi e power minus s t into sin t dt, and we will evaluate this integral in the normal process. This is equals minus cos of t e power minus s t 0 to pi, using the minus s into 0 to pi e power minus s t into cos of t dt. And if you see this one, this value we can find out from here. This I am keeping as it is, say, minus cos t into e power minus s t 0 to pi, whose value we can find out, minus, again we are repeating the earlier process by parts, and we can obtain s into sin t e power minus s t 0 to pi minus s square into 0 to pi e power minus s t into sin t dt. And if you see this integral e power 0 to pi e power minus s t into sin t dt, this is nothing but this right hand side integral. So, that we can take this one on the right hand side and this is nothing but your, this portion is nothing but your I only, this is your I. So, in the next step we can write down this is nothing but 1 plus s square into I, this is equals minus cos t plus s sin t into e power minus s t 0 to pi. So, you can put the limits of this, and this you will get e power minus s pi plus 1. Therefore, your I is equals to basically 1 plus e power minus s pi divided by 1 plus s square. So, that Laplace transform of modulus of sin t, Laplace transform of modulus of sin t, this is equals 1 by 1 plus s square into 1 plus e power minus s pi divided by the denominator will be e power minus 1 minus e power minus s pi. So, this is the Laplace transform of this modulus function of sin t, which is a periodic function of period pi. So, just again I am just repeating the process, so that you can understand it easily. We are evaluating the integral using integration by parts, you are getting it, and then you are obtaining I equals 1 plus e power minus s pi by 1 plus s square. Now, let us see another function which we call as a sine integral function. This is again sine integral function is defined as, we denote it as SIT, which is here we have written SIT equals 0 to t sin x by x dx, and the graph you see we have given of sine integral function, the graph is also given over there in the upper half here. If you see here, the graph is given. Now, we will try to solve this particular problem using various methods. I will try to show you that one particular problem can be solved using how many methods, and you will get the same result. Using integral theorem, we can solve this problem. Let us see. You know this thing, Laplace transform of 0 to t f x dx, this is equals f s by s, where f s is the Laplace transform of f x, if small f s is the Laplace transform of capital F x. So, Laplace transform of sine integral function of t, this is equals, I can write down 1 by s Laplace transform of sin t by t. Using this one, I can write down this is equals 1 by s Laplace transform of sin t by t, because if you see your f x, your problem sin I t was s I of t, this was 0 to x, 0 to t sin x by x dx. So, basically the function is sin x by x. So, using this particular theorem, integral theorem, I can say Laplace transform of sin I t is nothing but 1 by s Laplace transform of the function f t, where f t is your this. So, this is sin t by Laplace transform of sin t by t, which was f s. So, only thing I have to do, I have to evaluate the Laplace transform of sin t by t, and this I can write down again 1 by s to infinity 1 by x square plus 1 into dx. Using division theorem, that means divided by t, if I know the Laplace transform of a function, then if Laplace transform of the function which is divided by t will be 1 s to infinity 1 by was Laplace transform of this, Laplace transform of sin t is 1 by 1 plus t square. So, that this will be 1 by 1 plus x square dx, and this is nothing but 1 by s into tan inverse x, the value of the integral is tan inverse x where limit will be from s to infinity. So, this will be 1 by s into, if we put infinity, then it will be pi by 2 minus tan inverse s, and this I can write it as 1 by s tan inverse 1 by s. So, this is the simplest solution. If you see, just I am using this theorem over here, Laplace transform of 0 to t f x dx equals f s by s, the integral theorem I am using, and using the integral theorem I am writing this equals 1 by s Laplace transform of sin t by t. This Laplace transform of sin t by t, again by division theorem I can write it s to infinity 1 by 1 plus x square dx. So, ultimately it boils down to evaluation of the integral dx by 1 plus x square, and you are obtaining the result as 1 by s tan inverse 1 by s. So, this is your one method, as I told you. So, this particular problem using division theorem you are doing it, and you are obtaining the required result over here, that 1 by s tan inverse 1 by s, you are obtaining the result. The next one is using differential multiplication and initial value theorem. In the last lecture, we have done the initial and final value theorem also. The application of initial and final value theorem we will show by this one. So, let us see here, your f t is sine integral function of t. This is equals 0 to t sin x by x dx, this you know, and we are assuming that Laplace transform of f t is equals to say f s. This always you can assume. So, your function is f t equals the sine integral function, that is 0 to t sin x by x dx. So, from here if you try to calculate f 0, your f 0 will be equals to 0. From this integral always you can write down f 0 equals 0, and your f dash t, this is equals to sin t by t. Using the Leibniz integral rule, always you can tell from here directly you can tell that your f dash t is sin t by t. So, once I am getting f 0 and f dash t, therefore, from here you can write down t f dash t, this is nothing but your sin t. Once I am getting this t f dash t equals sin t. So, taking Laplace transform on both side of this, Laplace transform of t f dash t, this is equals Laplace transform of sin t, or Laplace transform of t f dash t, this you can write it as minus d ds of Laplace transform of f dash t, which is equals 1 by Laplace transform of sin t is 1 by 1 plus s square. So, once I am getting this one, basically this we obtained using multiplication theorem. The multiplication theorem what we got from there, I wrote it as minus d ds of Laplace transform of f dash t equals 1 by 1 plus s square. Again, d ds of Laplace transform of f dash t, this you can write down s f s f dash t equals Laplace transform of f dash t is s f s minus f 0. This is equals, this minus I am bringing on the right side, so that it becomes 1 by 1 plus s square. So, d ds of this equals to 0. So, d ds from here, d ds of s f s, d ds of s f s, this part will be 0, and this is equals 1 by 1 plus s square. This f 0, d ds of f 0, since it is a constant term, so it will be 0. So, now from here if I integrate on both side, I will obtain from this one, next step will be s f s, this is equals to your minus tan inverse s plus c. This is integrating on the both side. On the earlier equation I am getting s f s minus tan inverse s plus c. Now, you have to find out the value of c. Here comes the role of the initial value theorem. if you remember that limit s approaches infinity, SFS, this equals to limit t approaches 0, ft. Limit t approaches 0, ft is f0, and already we know your f0 is 0, or in other sense whenever s approaches infinity, your SFS is 0. Once I substitute this as s approaches infinity over here, if you make as s approaches infinity, this value turns to 0, this value will be 0. So, that you can say from here that C equals 0. So, that from here you can tell that your Fs is nothing but 1 by s into pi by 2 minus tan inverse s, and this is nothing but your again 1 by s tan inverse 1 by s. So, here actually you are using the concept of initial value theorem to find out the value of the arbitrary constant, and you are getting the same result over here. If you see quickly on this, your f t is this. So, that using Leibniz integral rule you can obtain f 0 and f dash t. Leibniz rule I have written, those who have forgotten you can check it afterwards, and from here t f t f dash t equals sin t. So, that Laplace transform of t f dash t equals Laplace transform of sin t. So, using multiplication theorem you are writing this, then using differentiation theory Laplace transform of f dash t you are writing SFS minus f 0, and this equals you are writing this SFS you are obtaining. Once I am obtaining SFS, now I am using the initial value theorem as s approaches infinity, this one, since I got SFS equals tan inverse s plus c. So, I am obtaining this, sorry, in the I told wrongly, your c will be in that case pi by 2, because as s approaches infinity, your tan inverse s, that value will be pi by 2. So, that c will be pi by 2. So, Fs will be 1 by s into pi by 2 minus tan inverse s, and the result will be 1 by s into tan inverse 1 by s. Now, method 3 is using infinite series. Just this I am just telling like this. Sin x I can express in terms of infinite series like this. Once I am expressing this, so that multiplying dividing by x I will obtain this one, 1 minus x square by factorial 3 x to the power 4 by factorial 5 minus x to the power 7 by factorial 7 like this, and I can integrate it very easily. If I put the values, I will obtain t minus t cube by 3 into factorial 3 t 5 by 5 into factorial 3 like this way, and once I am doing it. So, now I can take Laplace transform on both sides, because I obtained 0 to t sin x by x is t minus t cube by 3 into factorial 3 like this. So, on this taking Laplace transform on both sides, if I take using linearity property, I know it that Laplace transform of a f t plus b g t equals Laplace a into Laplace transform of f t plus b into Laplace transform of g t. So, that I can break it all this, and I know the Laplace transform of each of them. As I have written here, Laplace transform of t power n is equals to factorial n by s to the power n plus 1. So, that I will obtain all these values. This already we have done how to find out, and this again I can write it in terms of a series like this, and this equals nothing but 1 by s tan inverse 1 by x, because tan inverse x the series I have written x minus x cube by factorial 3 plus x to the power 5 by factorial 5 like this way. So, if you see, I am solving the same problem with various methods. The fourth method which I will show you, that is using substitution. Let x equals t v I am writing. So, that 0 to t sin x dx can be written as 0 to 1 t v by v into d v. So, once I am writing this, taking Laplace transform on both sides, I can write down this thing. Once I have written this using the definition of Laplace transform, I can write it 0 to infinity e power minus s t into 0 to 1 sin t v by v dv into dt. I can change the order of the integration without changing the property, so that I can interchange the dv and dt. In the earlier case it was dv dt, now I am changing the order, so that it has now become dt into dv, 0 to 1 by v into this, and this equals 0 to 1 Laplace transform of sin t v by v. So, because e power 0 to infinity e power minus s t sin t v dt, this is nothing but your this one. So, I am getting 0 to 1, just I am doing the problem from here itself. I am getting 0 to 1 Laplace transform of sin t v by v into dv, and this is nothing but 0 to 1. You know Laplace transform of sin t v is which one? Laplace transform of sin t v is equals to 1 by s square plus v square. So, that it will be dv by s square plus v square, and once I am writing this, I know the value of this, that is 1 by s tan inverse v by s, the value is 0 to 1, and this again if you evaluate the integral, you will obtain tan inverse 1 by s. So, if you say we are getting the same result using this property, and if I come back to this, so this is equals to 0 to 1 dv by s square plus v square, and which is nothing but 1 by s this thing, and we got the result. So, same problem we are solved in 4 different ways. So, whichever looks simpler, using that one I can find out the Laplace transform of some functions. Now, let us take another function, the similar function, which we call as cosine integral function. The graph you see here, the graph is like this, it is going like this and it is moving across like this, and cosine function is defined by CIT equals t to infinity cos x by x dx. Now, the solution procedure will remain same, that is, suppose your f t is CIT t to infinity cos x dx and Laplace transform of f t is f x. So, f t equals minus cos of t by t, f t f dash, sorry, not f t, but f dash t equals minus cos t by t you will obtain. Once I am obtaining this, from here I can write down t f dash t equals minus cos t, and from here I can write down, taking Laplace transform on both sides, Laplace transform of t f dash t equals minus Laplace transform of cos t. Using the multiplication theorem, just like the earlier approach, Laplace transform of t f dash t can be written as minus d d s of Laplace transform of f dash t, and this is equals minus s by s 1 plus s square. Laplace transform of f dash t can be written as again s f s minus f 0 using the differential theorem, differentiation theorem. So, ultimately I am getting d d s of s f s, this is equals s by 1 plus s square. So, that if you evaluate the integral, you will just integrating on both sides, you will obtain s f s equals half into log of s square plus 1 plus a constant term integrating on the both side. Now, here again I have to find out the value of the constant of integration c, that is, using final value theorem, Laplace transform a limit s approaches 0, limit s approaches 0 s f s, this is equals limit t approaches infinity f t, and which is equals to infinity cos x dx. So, that the value becomes 0, or in other sense, using this I can obtain the value of c as 0, and therefore, the f s equals 1 by twice s into log of s square plus 1, which is the function, which is the Laplace transform of the cosine integral function. Now, let us take another function, that is exponential integral function. The graph is given of the exponential integral function, which is defined as E t equals t to infinity e power minus x by x dx. So, you are writing f t from here, and if I write down f t equals here, I will check that your f t equals your E t. I am just writing t to infinity e power minus x by x dx, and your Laplace transform of f t, this I am assuming as f s. So, that f dash t using the Leibniz integral rule, you can write down minus e power minus t by t. Once I am obtaining this from here, again t into f dash t, into f dash t, this will be equals to minus e power t. Now, I will follow the similar process from here, that is, so let us go back to the next slides. Using this, I am getting this, taking Laplace transform on both sides of the given equation. Laplace transform of t f dash t equals minus Laplace transform of e power minus t. So, that using the multiplication theorem, following the same theory, minus d d s of Laplace transform of f dash t is this, and Laplace transform of f dash t you are replacing by s f s minus f 0 by differentiation theorem. So, that you can obtain after integration s f s minus log of s f s equals log of s plus 1 plus c. So, limit s approaches 0, s f s is limit s approaches infinity f t, and the value will be 0. So, that again the value of this function, the Laplace transform of given function will be equals to log of s plus 1 by s into log of s squared plus 1. So, these are some special functions whose Laplace transform we are trying to derive. In the next lecture also, we will initially start with some more special functions, which are very useful in various engineering problems, in statistics and in other places. So, we will try to see what are the Laplace transform of those useful and frequently used functions, and this we will cover in the next lecture.